Coming up on Science Works. Microsoft has already changed the world when it comes to video games, computers, and other technology, but they're not done revolutionizing yet. We'll see how one of the most innovative companies of all time is planning ahead for the next generation of big ideas.
The entire world was transformed when Microsoft introduced Windows to personal computers. Since then, they've been at the forefront of technology, inventing the Xbox, Microsoft Office Suite, tablets, the list goes on. But the more exciting question is, what's next? We're here at the Microsoft headquarters in Redmond, Washington, to take a look at some cool ways developers and designers are inspiring the next world-changing technologies. I never would have thought a visit to Microsoft would have us climbing up into trees, but the company has built these cool tree houses for employees to use. They believe that creativity can happen anywhere, from a traditional office to this amazing location, fully equipped with electricity and Wi-Fi. Karen Weber is the director of the Education Workshop here at Microsoft. Karen, we're in a treehouse. This is so cool.
And there are actually 3 tree houses here on the Microsoft campus. And what we have found is that Microsoft wants to support employees being creative and innovative any way they can. So get out of the offices, come into inspirational places, be up here in the tree, and start to actually try and do some work and be creative.
And now you're the director of the Education Workshop. What does that mean?
Well, technically, I'm a designer. And I've spent my whole career really thinking about how people do things in the world and designing interactions for people to be able to do that. So along the way, I've invented ways for people to be able to have experiences.
So now you're at Microsoft, and what types of tools are you using here?
Well, I'm very lucky that I actually get to work on education tools for students that are from kindergarten up until about 12th grade. And we're looking at a suite of STEM tools, tools that will help teachers bring science, technology, engineering, and mathematics into their classrooms. This first project looks at learning about earthquakes using computational thinking. And the first thing that students do is they build an analog model of how S-waves work.
S-waves are earthquake waves that shake the ground up and down and side to side, perpendicular to the direction the wave is traveling. This motion is what causes the most damage to buildings.
And the interesting thing about S-waves is that they come back. So they come in, if you can see, the wave comes and it comes back. So this transverse wave machine is made simply with a little bit of ribbon, some skewers, and some gumdrops. What's important is it gives the students a way to visualize and learn about those waves in a really hands-on way. We're talking about concepts that are hard to see. You know, when I think about an earthquake, I can see the damage, but it's really hard to understand how the shaking happens. So once students understand the concept, the next thing they do is they build a seismograph.
A seismograph is a tool that is used to measure the intensity and duration of earthquakes.
Now this seismograph is made with a paper plate, plastic cup, a spool, some string, and what happens is it's connected here to this little microcontroller. So now we've moved from the analog to the digital, and you can see that when I start to shake this, I can actually generate a seismograph.
Oh, cool, and you can see it on the computer too.
Right, and you can see how those plates are moving. Now, what's really interesting is now thinking about how students take that knowledge of the waves and translate that into a real-world experience. So the next thing they do is they build a model here of Taipei 101.
Taipei 101 in Taiwan used to be the tallest building in the world and had a heavy steel ball hanging inside the middle around the 90th floor. The 660-ton ball is known as a tuned mass damper, which reduces movements and vibrations caused by wind and earthquakes.
And what we have students do is actually model that by building this representation of the Taipei 101. So what we're going to do is we're going to run this with 2 trials.
Okay.
First, without the 660-ton ball, and then the second time we'll run it with. Now, the quick thing to do is to make sure that we actually run exactly the same. So we're going to run it up here to 20.
Okay.
If you want to count us.
Yes.
3, 2, 1, go! Earthquake. You can see our earthquake was recorded.
Oh yeah, you can actually see it on the computer.
On the computer with the graph. Okay, so let's do this again, but this time we've added our tune mass damper. We have some washers on here to provide the weight, acting as our 660-ton ball. Ready?
Ready.
So we're gonna run this up to 20. We'll count 3, 2, 1, go! And you can see that it almost shuts it down immediately.
I can see on this graph that the blue line goes completely flat after, while the pink line keeps having curves.
Right, so the pink line was without the tune mass damper, and the blue line is with. So you can see how you can mitigate earthquake damage and see the data to actually support that. And thinking about how we can help people, while you can't stop earthquakes, the fact that you can use engineering to mitigate earthquake damage is a great advance.
What's the goal for projects like these?
Well, if you think about it, 65% of all future jobs are yet to be invented. There are students today working at Tesla, and that used to be science fiction. We are now at the point where we have students going to be taking on new roles and need new skills. So these projects, by the time a student is done, they have done some mechanical engineering, electrical engineering, software engineering, and data science. And our hope is that we're seeding them with these new master skills that will help them be inventors and the creators of tomorrow.
What's this tool for over here?
Well, this is our lesson plan called Machines That Emulate Humans, and it starts off first with an anatomy lesson, and the students learn about the bones in their fingers. Now, these are actually called phalanges, and we have the medial, the distal, the proximal, and the metacarpal, and those are the phalanges. Now, the first thing they do is they actually build an articulated model of their finger using this fat milkshake straw or boba straw, a little fishing line, some felt, and a paper clip. And you can see,
Cool.
you can actually see that you can study not only how your finger moves, but actually have this lovely little model.
Can I play with it?
Of course you can.
Ooh.
The next thing that the students do is they build this sensor. That if that's the robot, then this is the control. The sensor is made simply out of some copper tape. It's on some cardboard, and there's some conductive material called Velostat underneath. And what's super cool is when I hook this up back to a little microcontroller and put my robotic finger up there, I can actually now start to have a machine that emulates a human.
Wait, can I try that one?
Of course you can. But actually, let's try that.
That is so cool.
Now, this is very low cost to make. Remember, that's just a straw with some fishing line, a little bit of cardboard, scotch tape, a little bit of conductive material, and you can make these things. Now, 5 students, they make 5 robotic fingers, 5 sensors, and what you now can get is a whole hand. Why don't you put that on? Open and close, and you can see that it's measuring different flexions and extensions for each of the fingers, plus calculating the X and Y coordinates that the thumb would need versus, in this case, the proximal or the metacarpal.
That's really cool. A few students decided to take the basic components and technology used to create this robotic hand to make a cool robotic creature.
What they did was they took the exact same code that worked on the hand that you saw in a moment, and if you put this on, they built themselves an articulated dragon. And what you'll see here is all the same fundamental principles, the same kind of movement of the wings are actually the same fingers that moved the hand before. And if you hit the index finger, the head should come up, and we can actually get the neck to articulate.
After learning about all these neat STEM projects from Karen, I wanted to talk to some of the students who work on these in class to see how they're applying the concepts to real-world ideas.
This is so cool. What's your name?
I'm Emily.
You created this dragon?
Yes, me and a group of my friends.
What made you think of this project?
Well, we were working on the bionic hand project. Personally, as a dragon fan, I go, hey, wouldn't it be so cool to make a dragon move like this?
So how does this hand control that dragon?
So the thumb controls the neck, and the pinky controls the mouth. The index and the ring finger control the wings, and the middle finger controls the tail.
What was the process behind building a dragon like this?
We had to see what was going good, what was going wrong, and then decide what is our best way to fix this. For the wings, for example, we were looking at this going, how are we gonna make these extend? We saw this cool video online about these wings that are like this, and it looked almost like a car jack almost. And so we looked at that, and we decided to make it out of popsicle sticks and mini brads.
That's so cool. I feel like also dragons are very in right now.
Yeah.
Let's meet our STEM hero. Bridget Meigs manages the farm at Stonehill College in Massachusetts.
I'm Bridget and I run the farm at Stonehill. The farm at Stonehill is a living classroom, but it's also a community farm, really a mission-driven farm. So what we try to do is everything we grow, we donate to a mobile market in the city. The focus of this farm is hunger, and we're teaching about how do we grow things sustainably and then how do we feed people sustainably. I personally did not think I was going to be a farmer when I was little. The reason I'm here is because the issue of hunger, both local and global, is really something that shakes my core. At the farm, we definitely have STEM in action. There's this science that's happening, thinking about, what do the plants need? How do we grow them best in terms of their resources with water? The math is happening, thinking about if we harvested 120 pounds of cucumbers, which happened today, where should this go where it's going to find a home and be eaten today or tomorrow and not go to waste? There's this awesome ability to both kind of work with science and grow better fruit and vegetables and get it out to more people.
Bridget Meigs is this week's STEM hero.
I'm here with Ankur, who runs the business side of things here at Hacking STEM. What does your job entail?
At Hacking STEM, our mission is to democratize STEM. And by democratizing STEM, I mean keeping STEM affordable and available to everyone. And we do that in two ways. One, by keeping the cost down, using everyday materials. And second, by leveraging partnerships. And I'm proud to talk about the Mattel Hot Wheels Speedometry partnership today.
This is so cool. We actually have a racetrack and Hot Wheels cars. What is this for?
This Hot Wheels track has been hacked by my team. And the Mattel team was very generous to allow us to hack the track and the car.
Hacking, in this case, means making changes to the original equipment in order to adapt it for your own needs.
So what you see here is 9 gates, 9 cardboard gates. Each gate has these stranded wires hanging down. And when these gates touch the hacked Hot Wheels car, which is simply putting a paper clip at the back of the car, this acts like a switch. And when this switch touches this gate, we get this signal in Excel.
So what you're telling me is this little paper clip touches these wire things that hang down, and it gives a signal back to the computer?
Exactly. So it's acting like a switch, and this is a trigger. Whenever this touches the switch, there's a trigger, and that timestamp gets generated in Excel, and what we are measuring is speed of the car, energy in the system, which is potential energy and the kinetic energy, and the lap time.
Remember, energy cannot be created or destroyed. All energy in the world exists as potential energy, which is stored energy, or kinetic energy, which is energy of motion or speed.
So when I run this down the track, you'll not only see the speed of the car, you'll also see this potential energy graph going down. As the potential energy is highest in the system when the car is still, it gets converted into kinetic energy when the car goes down. So that transformation of energy from potential to kinetic is hard to visualize for kids. But in this system, they can actually see that graph in real time.
So can we see this actually go through the gates?
Sure.
On your mark, get set, go! Woo! So what do these numbers mean on the screen?
So we had 9 gates. Car passed through each gate, and we have timestamps of each gate on the bottom.
The 9 gates are used to create a graph showing the potential and kinetic energy in this racetrack system. When the car is at the top of the track, the potential energy is at its highest. And as it moves down the track, it gets converted into kinetic energy. Notice as potential energy decreases, kinetic energy increases.
You also see how there's a small funk in the curve when the car goes through this loop. At one point in this loop, the potential energy is again at the high, and when it goes through, it turns back into the kinetic energy. And that explains sort of a funky little curve in the middle.
Does it change when you have different cars?
That's a great question. What the students do next is sort of add washers to increase the weight of the car. And then they understand the relationship between the mass of the car and the speed of the car and the energy in the system.
So can we see how this car compares to the other car?
Yes. So as you see, we have added some weight to the system and some washers. And
on your mark, get set, go! Oh no, what happened?
The weight was too much. So after a point, the weight acts counterproductive. Rather than adding to the mass of the car and helping it go through the loop, it actually makes the car not complete the loop and fall off the loop.
Do the students end up finding the perfect weight of the car to make it go the fastest?
That's the goal. And they do trials, and the goal is to come on top of the leaderboard and hit the lowest lap time.
Oh, that's really fun. So they get to compete against each other?
It's a competition in the classroom.
Yeah, that sounds awesome. This is a cool way to learn about energy. What inspires you to do this type of work?
So I was born in India in a very low resource setting, and both my parents were teachers. And ever since I can remember, they always told us that only education can help us realize our dreams. So education is very important to me and close to my heart. So I'm inspired by helping students to achieve more by using everyday objects and keeping STEM affordable and accessible to everyone.
I'm here with Life, who's a data scientist. What is data science?
Data science, that is actually making sense out of data. Getting data, analyzing data, and visualizing data.
So what do we have here in front of us right now?
This is a set of glasses, 1 to 5, all containing water. They look the same.
Right, they look exactly the same.
Right, there's no difference, right?
Even though each jar of water looks the same, there's a significantly different amount of impurities, or total dissolved solids, within each sample. Total dissolved solids measures the combined minerals, metals, salts, and other organic and inorganic substances contained in a liquid such as water. With this test, water can be collected from nearby ponds, lakes, or rivers, and then by measuring the electrical conductivity, we can determine the impurity levels.
This is a straw, as you can see, and you have in here 2 sticks and 2 wires. So we can measure the current between these wires, that's all it does.
You may be surprised that pure water doesn't actually conduct electricity. Electrical current can only flow when there are electrons or ions present. Tap water, rainwater, and seawater all have various impurities such as salt, magnesium, and calcium ions. So the different levels of these impurities determine how strong the electrical current is in the water. Water that is heavily polluted will have even greater amounts of impurities, so the electrical conductivity will read higher.
You dip it in the water and you will see now the tool basically measuring how much current will come through the water. So in this case, we will see after a while that we're missing in the 270 parts per million, which means that in a drinking term, it's marginally acceptable.
Yeah, you can see on that graph right there that it's purple, so that means marginally acceptable. So can you drink it or can you not drink it?
You want to try? No.
Yeah.
No.
Wait, can I try dipping it in different waters?
Yes, let's do that. And then number 5 is kind of more industrial zone in this case. So let's try it there.
So you dip it in.
And now you see it's pretty high, right?
No.
So this is basically a very high maximum stuff. Don't drink it.
And you can test all types of water just by doing this?
All types of water, yes.
Why is it important for kids to do it this way by measuring instead of just reading a graph on the computer?
The application of feeling and seeing something and actually seeing the graph afterwards, this makes it more real for people. This is my water. I took the water from my drinking area, right? And that makes it real for me. Versus just reading a number on the graph doesn't mean so much for me.
With all these experiments, you actually bring them into classrooms, right?
That's right. That's the whole point of hacking STEM.
I want to go try one in a classroom.
Let's go.
Cool. I'm here with Jason Ewert. His students are actually doing some of the experiments we just saw. Jason, what's it like teaching a class like this?
Well, this is basically a dream job. So, I have the very cool opportunity to teach STEM elective classes, so science, technology, engineering, and math, and kids choose to be in my class.
How do you create age-appropriate experiments for these kids?
Well, it's been fun. I've been working with the Hacking STEM team at Microsoft, and we've been working together and collaborating, and it's really, really fun as a teacher to have ideas for a project, but then have the muscle and the brain power of Microsoft engineers and designers and data visualization experts to actually help us take it to the hoop.
Do you think it's really important for students to actually see the experiment in front of them instead of just learning it through a textbook?
Yes, it's very, very important for students to be able to visualize what they are working on, and so live data is where it's at. Students can actually look and see how their device is interacting with the environment and then see these different visualizations of what's going on Excel. And it really helps them understand what is going on with their device. And then it also helps them to think of new and creative and different ways that they can actually communicate information about the world around them.
What are you learning about right now?
We're measuring the electrical current in the water.
How cool that you get to learn this hands-on experience.
It's so cool.
The more electricity it can conduct, the more pollutants the water has.
We're learning how to make sensors that are really cheap, so it's really good for all those countries that are not as wealthy as our own. And so it tests the water pollution level so that we can make it so people will drink better water.
In the future, the world is going to be run by kids your age now. What types of things do you think would be cool for you to invent?
Probably things that can prevent pollution, because then it can improve the amount of wildlife and save animal lives, and it will actually make the environment much safer for us and for the animals.
So the type of environmental work you're talking about is similar to the work you're doing in class right now.
Right.
As my students get a few years older and start entering the workforce, they're going to be entering a world of the unknown, where 65% of the jobs that they are going to be looking at don't even exist today. And so if we can get kids into the mindset of taking all of their available resources and integrating those creatively, they can solve all kinds of problems.
So they can change the world.
Yes.
Your students are going to change the world.
I can't wait.